All right, so two bits of information. The first one is there's no labs this week, so anyone who's scheduled for lab today, we don't have it after this. But I'd be happy to talk to you after, we can go into the lab and talk if you want to, ask any questions or go over problems or whatever. And then the second thing is lab exam 1 is, I believe, tell me if this sounds wrong. I should have looked at the syllabus before I came, but I think lab exam 1 is next week in your lab. So let me just make sure. Okay, lab exams. Yeah. So Monday, February 26th, and Wednesday, February 28th. We've had 3 labs so far, and so this test is just going to ask questions like those 3 worksheets that you did. And so the topics are, we did that one that was called preliminaries or something, just some of the skills that we were going to use later. And then we did the one on position versus time graphs. And then we did the one on vectors. So that's all you have to be ready to do for this, is to be able to answer questions like the questions in those. Anybody have any questions about that? What it's going to be like or anything like that? It's not going to take anywhere near the full period, and when you're done with it, you're done for the day. So you'll have plenty of time to think about it and stuff. Okay. And then what we've been working on, we started talking about 2D particle kinematics. And so now we're doing everything with vectors. And what we worked to eventually was the 2D constant acceleration equations. Okay, and in 1D, there are 3 constant acceleration equations, and those are this, this one, and 2a times the quantity pf minus pi is equal to vf squared minus vi squared. And in 2D, the way this works is position initial, position final, velocity initial, velocity final, and acceleration are all vectors. And so all of these equations have components for these vector variables. And so there's an x component equation for this one, and then a matching y component equation where instead of the x components, you just have the y components. And same with this, x, 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 x. And then there's one with the y's, and the same with this one. And remember that The one thing that's not a vector that doesn't have components is time final in these equations. And I gave you a set of steps for going through these that pretty much just mirrors. It's, sort of a extended set of steps that from what you did in one dimension. And so today we're just going to go through some problems. And then after we go through, I think I'll probably go through 2 problems, and then we'll get to a point that I want you to remember. So let's start with this one. So let's say that an object is launched from a height of 1 meter. And it's launched at an angle of 40 degrees above the horizontal. Okay, so an object is launched at 40 degrees above the horizontal. With a speed of 10 meters per second. From a height of 1 meter. What is the object's position when it reaches the highest point, its highest point? And then just because this comes up every once in a while in questions, and I haven't really talked about it much in class, let's also figure out what's the displacement of the object from its starting position to when it gets to the highest point. So what's the object's displacement vector from its start point to its highest point? Okay, well, what's this thing going to do if it's launched like this with a speed of 10 meters per second? It's going to follow a path like this. All projectile motion in 2D follows some sort of parabolic path. Okay. And we're going to try to figure out what's going on here when it reaches the highest point. Okay, I'm going to just go through this step by step to try to help you sort of ingrain these steps. I think you'll be happy if you get in the habit of following these steps. Just sort of make it, internalize it, do every one of these problems the same, and it'll keep you from making a lot of dumb mistakes, I think. So the first step is you have to choose where your origin is going to be and how your coordinate system is going to be oriented. And then you have to choose an instant you're calling time equals 0 and an instant you're calling time final. Okay, so I'll put the coordinate system down here. I always just put the origin of the coordinate system on the lowest spot in the problem, so to us, that's the ground in this case, right underneath where the object is at the start of its motion. So I'm going to use this coordinate system with x like that and y like that, and I always have my y-axis pointing up. Now we have to choose the two instants. What are we going to choose as the instant time equals 0? Yeah, start of the motion, yeah. And the reason that we're going to do that is we have information there. We have information we can use to find a velocity vector. We have information we can use to find a position vector, okay? So we want to choose these instants so we can take advantage of the stuff we're given. So time equals 0 is going to be the instant it's launched. And what's time final going to be? Yeah, when it reaches the highest point. Exactly. And now we want to figure out what variables we know and what variable we want to find. And I'm just going to go through the list of variables. So first of all, do we know time final? Do we know if you turn the stopwatch on when the thing is launched, do we know what the stopwatch says when the object reaches its highest point? We don't know that, so I'll leave that off. Do we know the acceleration vector? In free fall problems, you always know that. If your y-axis is pointing up, this acceleration is always going to be 0 for x, negative 9.81 for y. Do we know the position when time is equal to 0? Well, remember that the position vector you can think of as just the coordinates of the object. So what we're trying to figure out are the coordinates of that point right there where the object starts. Based on the coordinate system we chose, the coordinates of that black point are 0 for x and then positive 1 for y. So that's P initial. Do we know anything about P final? That's what we're trying to find. So I'm going to write this over here. Even though you can only solve for, you can only solve for one variable at a time, we're going to try to do both of these eventually, so it doesn't matter what order we go in. I'll just write them both over there. Do we know the velocity at time equals 0? We don't automatically know it, but we do know that, okay, so we are going to be able to figure out the initial velocity. And this is going to come from thinking, okay, here's our coordinate system. And our velocity vector is in this direction, where this is 40 degrees. And it has a magnitude of 10. And we want the components of that. So to get the components of that vector, you want the angle, the counterclockwise angle from the positive x-axis to the vector. So what's that angle? It's actually the one that's given in this case. It's not always that simple, but in this case, if you're starting at the x-axis and going counterclockwise until you hit the vector, you're going positive 40 degrees. So this is going to be, give myself some more room. So this is going to be 10 times the cosine of 40, 10 times the sine of 40. And that comes out to be 7.66, 6.43. You're almost always going to have to do that on these problems. You're going to have to use information about the speed and at some kind of angle to figure out what the components are. And then the last one is, do we know anything about V final? Do we know anything about the velocity when it reaches the highest point? This is like your time to shine. Every single time a problem asks you about the highest point, there's a fact that you know you're going to use. Yep.
Zero, but didn't you say something about two dimensions that not always zero?
Not the whole thing is zero.
Does it mean that the velocity is zero?
Yes, but not the whole velocity vector. One component of the velocity, just the y component. So Vfy is equal to 0. We don't know what Vfx is. Well, it turns out, so this is kind of like an aside, just like if you're ever in a conversation at like a fancy cocktail party and you just want to impress people, the x component of the velocity is going to stay the same because there's no acceleration in the x direction. But for calculation purposes, don't write that down because it'll make you think that equations are going to work that don't. It's just everything works out nicer if you don't write it down. Okay? So that's only for cocktail parties. And if you're under 21, no cocktail parties. Okay. All right, so now we're done. We're trying to figure out both of these. It doesn't matter what order we go in. Well, what are we going to use? If all we wanted to figure out was PFY, we could use, we could use this equation. 2 times the y component of acceleration times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. You can see that works because PFY is in it, and then everything else in it. Hold on. Everything else in it is known. Okay, so we know AY, we know PIY, VFY, VIY. So this one will work. Another way you could go if you're sort of thinking ahead is, well, we could use TF to solve both x and y equations. So maybe right away we want to start by finding TF, you know. But let's just use this one first, solve for PFY, and then go from there. Okay, so we have 2 times negative 9.81 times the quantity PFY that we're trying to calculate minus 1 is equal to VFY squared, so that's 0 squared, minus VIY squared. VIY is 6.43. So minus 6.43 squared. Okay, so negative 19.62 times PFY minus 1 is equal to negative 41.34. Divide both sides by negative 19.62. And you get PFY y minus 1 is equal to 2.11. Now add 1 to both sides, and you get PFY is equal to 3.11 meters. Okay, so that's the height off the ground when it reaches the highest point. But we still haven't figured out how far it's gone in X, and we have to do that. Anybody have any questions about that first part? Okay, so now, we still know all this stuff. I guess now we know one more thing. And we'd like to figure out PFX. So is there an equation that works for finding PFX? It turns out there isn't yet. So PFX, no equation works. So what do we do if there's no equation that works? Cry? Oh, yeah, right. I didn't give you enough time. Yeah, so solve for TF and then try again. Usually that'll fix the problem. I mean, always in this class, that'll fix the problem. Okay, so what can we use to solve for TF? We can use this equation. VFY is equal to VIY plus AYTF. It has TF in it and everything else in it is known. So VFY is what? 0? VIY? 6.43, we just used that. AY? Perfect. Negative 9.81, and then we're solving for TF. And so 9.81 TF is equal to 6.43. And so TF is equal to 6.43 divided by 9.81. And so 0.66 seconds. And now that we know TF, we can use this equation. PFX is equal to PIX plus VIXTF plus 1/2 AX TF squared. So PFX is equal to 0 plus, what's VIX? Yep, right, 7.66, and then TF is 0.66. And then be careful with this one, because we're used to, in free fall problems, putting the acceleration as negative 9.81, but this is the x component of acceleration, so what's this? 0, and 0 times anything is 0, so this whole term goes away. And so we get that PFX is equal to 5.02. And so all together, what we figured out is in our coordinate system, the final position is 5.02, 3.11. And that's in meters. And remember that what that is that tells you the coordinates of the object when it reaches the highest point. So like if you drew your coordinate system, the thing starts here at 0, 1, and it ends 1, 2, 3, 4, 5, 1, 2, 3. It ends somewhere like here. That's the highest point. And it follows a parabolic path between those 2 points. Okay? And then what about the displacement? We've done all the hard work. The definition of the displacement vector is just the final position minus the initial position, the later position minus the earlier position. So this is just 5.02, 3.11 minus 0, 1. And so the displacement vector is 5.02 for x, 2.11 for y. Okay? Any questions about that problem? Okay, let's do one more. And I'm going to give you some time to work on this one too as you try to put this stuff together. So the second problem is this. Okay, so let's say that you have, this is for your YouTube channel. So you're on a skateboard. And you're traveling at 5 meters per second. And you're going to drop a ball or a coin or something. That's you. Okay, so you're going to drop this thing, right? And what you're trying to accomplish here is there's like a cup on the floor, okay? That has a height of 0.15 meters. And if you drop the ball from a height of 1 meter, you want to know how far away from the cup you need to drop that ball so it lands in the cup, okay? I mean, you can imagine this is going to go crazy on YouTube if you can make this work, you know? Everybody wants to see this. Okay, so the question is, like, you're going to put tape on the floor somewhere so you know when to drop it. Where do you want to put the tape on the floor? Like, where do you want, how far before the cup do you need to drop this ball so it goes right in the cup? So how far away from the cup, do you drop the ball? Well, let's take a second to just understand what's going on first. Because I know to some people your intuition is like, well, if you're just going to drop it, like you wait until you're right above the cup and drop it. But remember that the rule is if you drop an object, at the instant you let go of it, its velocity is whatever the vehicle is, the velocity of whatever it's dropped from. Okay, so if your skateboard, you and the skateboard are moving at 5 meters per second, at the instant you drop this ball, it's also moving horizontally at 5 meters per second. And so it's not going to drop straight down. It's going to follow sort of a path like this, you know, a parabolic path. Are you with me on that? Okay. Well, let's choose, make those 4 choices so we all agree on that. And then I'm going to give you a little time to try to figure out what variables we know and what we're trying to find. Okay, so I'm going to choose, for my coordinate system, I'm going to put the origin on the ground right beneath where the ball is when it's released. So my coordinate system is like this, and my X is horizontal and my Y is up. And then what's going to be our time equals 0 instant? Yeah. So that's the instant it's released. And what's going to be the time final instant? Yeah, and so let's call that when it reaches a height of 0.15 meters. Okay. Okay, so now that we've made those 4 choices, take a couple minutes and see if you can figure out what variables we know and what variables we're trying to find. Okay, so do we know how long it takes to hit the cup? No. Do we know the acceleration? Yep. So the acceleration is 0 for X, negative 9.81 for Y. Do we know the initial position? So that's the coordinates of the object at time equals 0. Yeah, you can see that's right on the Y-axis. So X is 0 and Y is 1. Well, that's the same way it was before in the last problem. So this is 0, 1. Do we know anything about P final? We know that P final Y component is 0.15. And we're trying to find PFX. Anybody have any questions about that? Does that make sense? Okay, what about the initial velocity? Do we know the velocity of the ball at the instant it's released? It's the same velocity as the skateboard. So, you know, what's the velocity of the skateboard? Remember that you can think of it like this. Here's your coordinate system. And now put the tail of the vector at the origin. The velocity vector of the skateboard is this way, with a magnitude of 5. And so the coordinates of the head of that vector are the vector components. What are the coordinates of the head of that vector? What's the x coordinate? 5, yep. And then what's the y coordinate? Right. So 5, 0. So that's the initial velocity of the ball. And then v final. Do we know anything about v final? No. We're not going to write anything down. If you're at a cocktail party, you could tell them that v final x component is going to be 5, but we're not going to write it down. Okay. All right, so is there anything that we can use to find PFX? So take a couple of minutes now and see if you can solve for PFX. See if you can go through the thought process. All right, so no equation works. And so we're going to start by finding time final. Well, we can do that using this equation. PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So 0.15 is equal to 1 plus, what was VIY? 0, so this second term goes away. And then the third term is minus 4.905 TF squared. And I'll rewrite this as 4.905 TF squared is equal to, so I subtracted this from both sides, and now I'm going to subtract 0.15 from both sides. And if you divide both sides by 4.905 and then take the square root, you get the time final is equal to plus or minus 0.416 seconds. That's two answers. Which one do we want? We want the positive because time is always positive for us. And now that we've found this, we can plug it into this equation. PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. And so PFX is equal to 0 plus 5 times 0.416 plus, now AX is equal to 0, so this third term goes away. And you get that PFX is equal to 2.08 meters. So if you drop this marble or ball or whatever, exactly 2.8 meters horizontally from the cup, it's going to land right in there. Anybody have any questions about that? Okay. So now I want to get to the second common misconception in this class. I'm trying to bring these out as they come up. So this is something that people usually, their intuition about this is wrong. Anyone remember what common misconception number 1 was? Yeah, that's right. So yeah, that gravity makes heavier things fall faster. That's what people think. So I'll just write what's true. Gravity actually doesn't make heavier things fall faster. In fact, not all heavier things fall faster than lighter things. When it does happen that heavier things fall faster than lighter things, it's an air resistance effect. It's not because of gravity at all. Okay, so what about number 2? People often think, let's say it's often believed that an object's horizontal motion affects its vertical motion in free fall. The fact is, so let's say actually, the vertical kinematic components are unaffected by the horizontal components. Well, there are some examples where the horizontal motion of an object is important for its vertical motion, like an airplane, for example. You can't fly an airplane without any horizontal speed. Or a frisbee, there's definitely something about the flight of a frisbee that depends on the fact that it's flying. But those are cases where air resistance is important. Okay, and so in cases where air resistance is not significant, you can calculate all the vertical stuff without knowing anything about the horizontal stuff, and it'll be right. Okay, so here's what I'm going to show you. I'm going to show you a Mythbusters video. So here's the example that I'm going to use. So imagine that there are 2 people back to back. One person is going to fire a bullet. Okay? And the other person is going to just drop a bullet. Okay, so this is supposed to look like a bullet. That's, okay. It looks like Gru from Despicable Me. So if somebody fires, so a bullet is fired horizontally, at the same instant a bullet is dropped from the same height. Which of those two is going to hit the ground first? Most people's intuition tells them that the bullet that's dropped is going to hit the ground first, because something about the high horizontal velocity of the bullet that's fired out of the gun is going to keep it from dropping, you know? And it's not true. Probably that comes from the fact that when things are launched or thrown or whatever with a high horizontal speed, they're so far away when they land that they usually hit something first, you know? And they hit something that makes it look like they're not falling at all if they're moving really fast, you know? Like if you fired a bullet into the wall, it would look like it hit the wall basically at the same height that you fired it, you know? So you have this sense that it's not really dropping. But the truth is, the bullet that you fire is going to hit the ground at exactly the same time as the one that you drop. It's just going to hit so far away, you won't even see it, you know? It'll be hundreds of yards away or whatever. Okay? So I want to show you a Mythbusters video where they actually do this. You can actually see it happen. And keep this in mind as a way to remember this second misconception, that horizontal motion and the vertical motion are independent of each other in free fall. Okay? Is that loud enough? Okay, so the idea is, I mean, they were off a little bit, but very, very little. And there, plenty of experimental ways that their timing could have been off by that amount. So, imagine, so basically interpret that as like, as far as we can tell, they hit the ground exactly at the same time, How do I get out of this? Okay, is that surprising? Kind of. Maybe some people have heard of something like this before, but I think for most people, if you haven't heard about this, like an experiment like this, you just kind of have this natural belief that comes from childhood or whatever, that the thing that's moving horizontally is going to have different vertical motion than the one that's dropped. It turns out that that's not true. And it's easy to see calculation-wise that it's not true. So let's do these two calculations just to see, okay? So this is just saying, remember the Mythbusters video? And now let's do the calculation. So I'll start with the one that's dropped. And let's say it's dropped from a meter high and shot from a meter high, just to make things simple. So let's say that this distance is 1 meter, and that's the bullet, and we're just dropping it down to the ground. So I'm going to choose my time equals 0 to be the instant that it's dropped. Time final is going to be the instant that it reaches ground level. And I'm going to choose my 0 position because this is a 1D problem. It's not, there's no plane of motion. It's just moving straight down. So I'm going to put my 0 position here and my positive direction up. And then we'll go through the variables we know and want. We're trying to find time final. The acceleration is negative 9.81. P initial is positive 1 meter. P final is 0. V initial is 0 because it's dropped. And V final we don't know. And the equation that's going to work is PF is equal to PI plus VITF plus 1/2 ATF squared. So 0 is equal to 1 plus 0 minus 4.905 TF squared. So 4.905 TF squared is equal to 1. And if you solve this, you get that TF is equal to plus or minus 0.455 seconds, and it's time, so we want the positive one. Okay? So now I'm going to do the calculation to see how long it takes to hit the ground if it's fired horizontally. Okay, so this time, it's going to be fired from a height of 1 meter. Its starting velocity is horizontal, and let's, just to make it a round number, let's say that it's going 1,000 meters per second. Okay, and it's going to follow a path that starts out like that and then is in this very flat parabola. I'm exaggerating it just so you can see that it's a parabola at all. And it's going to hit the ground somewhere over here. Okay? But we're just trying to figure out the elapsed time from when it's shot to when it hits the ground. Okay, my time equals 0 is going to be when it's fired. My time final is going to be when it reaches the ground level. My coordinate system, I'm going to put the origin on the ground right underneath where it is at the start of the motion. And now we'll think about what we know and what we want. Okay, so we're looking for time final. The acceleration is 0, negative 9.81. The initial position is 0, 1. The final position, we only know the y final position component, but that's going to be equal to 0. If it's fired horizontally at 1,000 meters per second, what are the components of the initial velocity vector?
1,000 and 0.
Yep, perfect. So 1,000 for x, 0 for y. You can think of that this way. Take the coordinate system. The velocity vector, put the tail at the origin. And it's this long vector with a length of 1,000. And then the coordinates of the head of the vector would be 1,000, 0. Okay. So what equation is going to work? We can use PFy is equal to PIY plus VIYTF plus 1/2 AYTF squared. So 0 is equal to 1 plus 0 minus 4.905 TF squared. And now you can see we got, even though this was a 2D problem and the first was a 1D problem, we got the exact same equation that we did before. And so obviously the solution is going to be the same. And so time final is going to be positive 0.455 seconds. And notice that no matter what speed we gave this, it just never comes into the problem. All we used was y components, so this could have been 100 million and it wouldn't have changed anything. Okay? Anybody have any questions about that? Okay, that's it for today. I'll give you some more questions, 2D kinematics questions, and then we'll finish up with this next time.